Hello everyone. Previously we had discussed on the uh, important 8 algorithms, right? So almost correctly 8 algorithms. So basically array-based algorithms, right? So from today we'll be discussing on the string-based algorithms. Very important string-based algorithms. When I say string-based algorithms, you would have already guessed this one, right? So we'll be going with some of the very important algorithms, whether it may be KMP algo, whether it may be Z algorithm. So whenever I say KMP, the next thing that comes to the head is Z or the Z algorithm, right? So however you pronounce it. And we'll be going with some other important problems as well. So we'll be going around 10 important along with the Robin Corp algorithm and others, right? So this is fine. Now let's get into the definition part. First, we'll be going with the Knuth-Morris-Pratt, also known as the KMP algorithm, right? So let's get into the definition part first. So Knuth-Morris-Pratt or the KMP is linear time string matching algorithm. So this is string matching algorithm. Just keep this in mind, right? So this part is very important. This is string matching algorithm that finds all the occurrences of a pattern in a text by pre-computing a longest prefix that is also suffix table, nothing but the LPS or the failure function, right? So this is fine. So it uses the LPS to skip unnecessary comparisons. Again, it uses the LPS to skip unnecessary comparisons, achieving peak of n plus m time, right? So where n is nothing but the text length and m is nothing but the pattern length. This is fine. We're done with the KMP algorithm. So let's go with the explanation part, right? So first, just listen to this carefully, or just listen to this, because whatever we discuss here, the same thing will be implementing in the form of code basically. Just listen to this carefully. Just give me a second here. This is fine. So first, what we'll be doing here. So first we'll be going with a LPS array, right? So first we will be going with the LPS array. So nothing but the failure function, right? So for each pattern, index I, LPS of I, what it stores the length of the longest proper prefix of the pattern to I plus 1, right? So that is also suffix of the pattern I plus 1. Just remember this one, right? So first one, this is not proper, meaning it is not the whole string, right? Proper is nothing but it is equivalent to the not whole string, right? So this tells us where to resume matching in the pattern after a mismatch, right? So this one you will understand crystal clear when we write the code basically, right? So next what we'll do, we'll build the LPS. So we'll be building the LPS, right? So here LPS is nothing but the longest proper suffix here, right? So this is fine. So LPS is nothing but the longest proper suffix. So we will be building the longest proper suffix first. Then meaning we will be iterating the pattern once using the two pointer idea, right? So I scans the current position and keeps the track of current, this one. What do we call? Current matched prefix length. On mismatch, uh, if we fail, then we will fall back to the LPS, nothing but the length one, right? For the first one, like it is equivalent to the jumping to the previous possible prefix. So never decreasing I unless it is necessary. This is fine. So this is fine, man. Now again we'll be going with the next step. We'll be going with a search loop, nothing but we'll be scanning the text with I and the pattern with J. On mismatch, sorry, on the match, so we will advance both. So on mismatch, what we'll do, if j is greater than 0, then we'll set j equals LPS, nothing but the longest possible suffix of j minus 1. We will resume from the last safe position in the pattern. Else we will advance I. Simple. This what it avoids basically rechecking the characters in the text that we already matched. So we don't have to recheck the characters that we have already matched, right? So that it avoids this main algorithm, right? So we know this, right? So now what will be the complexity? Building LPS will be big of m basically, right? So building takes big of m and searching will be big of n, right? So total we have to go with the build as well as the searching both, right? So if you know the KMP, so we have to go with building as well as the searching both. So overall time complexity would lead to big of n plus m, and so for the space complexity it would be big of m, right, for the longest possible suffix. So I hope this part is completely clear. Let's try to understand the same thing with the help of the code. Let's start writing the algorithm. right? So just give me a second here. So first, as we had discussed, let's build the longest possible suffix, right? So I'll just go with def here, build. So this one will be LPS of, let me pass the P here, build possible suffix. So longest possible suffix, this is fine. P is nothing but the pattern string. The pattern string, just remember this one, don't forget. So the parameter that we have passed, P is nothing but the pattern string, right? So first let's go with the length of the pattern one. M, yeah, this is equivalent to the length of the P, length of the pattern. So the next, let's create the LPS array that is filled with the zeros, right? Meaning LPS equals, so this will be 0 into M. This is fine. 0 into M and not match. This is fine. Now, next, let's do one thing. Let's go with the length, right? So length is nothing but the length of the previous longest prefix suffix, right? So I'll just initialize length to 0. Now let's start from index 1 because LPS of 0 is always 0, meaning, so let me go with I equals 1. So now let's do one thing. Let's go with a simple while loop here. While I less than M, meaning here while I less than M. This is fine. Now if the current character matches character at the index length, then what we need to do, let's see the same thing. If the current character matches the character at the index length, so this is nothing but if p of I, sorry, Python, right? So we don't have to write the bracket here. P of I, if it is equal to p of this one length, why this is not showing length? This is fine, length. So now, sorry, I didn't give colon. What error this is showing here? Expected expression. Huh? While I less than M, I have written. So this is fine. Oh, this indentation. So sorry. Let me give P at this one. 1 second. What the heck is happening, man? Yeah, I have written correctly, right? So if P of I, nothing but if the current character matches character at the index length, P of I equals P of length. This we are making use of the comparison operator. This is also fine. So let's carry on with this one, man. Let's see that one later. So let's extend the current prefix suffix length. Nothing but length equals length plus 1. This has to be. So this one has to be length equals length plus 1. And also let's record it in the longest possible suffix. So I'll just go with the LPS of this one I have to pass I. This one, let me assign this one to the length. Basically, I'll just go with length. Final one will be I equals I plus 1. So we have to move to the next character. So else what we need to do, let's check the same thing. So else, so this one, uh, else we need to mismatch after some matches, right? So let's go with the simple if condition. If length not equal to 0, then we have to fall back to the previous longest prefix suffix value, right? So accordingly, uh, we have to fall back here this step somewhere. Just give me a second here. Current match prefix. Yeah, on mismatch, you fall back to the this one longest possible suffix length minus 1, right? Like jumping to the previous possible prefix, right? So we don't have to decrease I unless necessary. So this we know, right? So that's what we need to do here. So this one, if length not equal to 0, then we have to fall back to the previous longest prefix suffix value, right? So I'll just go with the, why length is not showing here. I have to type this one entirely. Length equals LPS of, let me do one thing, let me copy length here, length minus 1. This is fair. Next let's go with the one more else here. mm, this this is not even taking, man. Just give me a second here. Yeah, I have given flower bracket here instead of colon. That is the reason, man. So now mm, this one has to be while, until while everything is fair. So let me do one thing, let format the document once. This is fine. LPS length equals 0. I have given I indentation while I less than M. So this is fine. If P of I, P of length, so length I'm going with right here. What is expected independent block? Oh yeah, we are going with this one, right? This is fine. Length and for this one as well, we need to go with this one as well. So else, this is fine. Else within this one again, have to leave the space here. This is fine, and this also space. This is fine. Now, if length not equal to 0, again within the if condition we are writing, right? So one bracket has so many cosec chaos actually in the code. So this is fine, man. Now this is fine. Now let's do one thing. Uh, let's go with one more else here. So else we have already written LPS of I equals else. What else we are going with? While else length not equal to 0. So what we are doing? We are going with length equals LPS of length minus 1, right? So let's go with one more else here. So I'll just go with else here. This is fine. So this is not here, man. This is fine. Now, oh yeah, sorry, this has to be here itself. Now let's do one thing. So what we need to do here, if no prefix suffix found, then we have to set the longest possible suffix I to 0 accordingly with the accordingly with whatever we have discussed. So this one will be LPS of I. Let me assign this one to the 0. Also I equals I plus 1. This is also fine. Now let me remove this bracket. So this is causing this one chaos here. This is fine. So we have to move to the next character. So I equals I plus 1. Finally, we have to return the longest possible suffix, right? So I'll just come here. Let me return something. I'll just return LPS. Finally, we are done with the build method, right? So build function. So now let's go with the search function. So I'll just go with the def here. KMP search is fine. Let me pass two parameters. One is text, another one is pattern. Simple. Now let's go with a list. Nothing but basically what does search function do? It returns the list of starting indices, right? So nothing but it is zero based where pattern is found in the text, right? So that's what we need to do. So let's go step by step. Uh, just go with n equals. Let's consider n and m, a length of the text and length of the pattern here. So this one will be length of, let me pass text here. This is fine. M equals length of, let me go with pattern here. This is also fine. So let's do one thing. If m, this one, if it is equal to 0, then what I need to do? So let me return something, man. So let me return. This is also fine. So we went with the convention. What is the convention here? Empty pattern is equivalent to the no matches that is returned. So that is the reason I'm just going with the empty array here. Simple, right? So the next step here would be, so let me assign the LPS to the build. So we have already written the build method, right? So we don't have to write everything from the starting. So I'll just make use of the build LPS function, right? So sorry, not the method function. So let me pass the pattern here. This is fine. So we have already pre-computed the LPS array. So let's make, we have made use of the same build LPS or the build longest possible suffix here. This one function here, right? So within the KMP search function. So what does the build basically do? It pre-computes the longest possible suffix array, right? So now this is fine, man. We have idea on this. So now let's do one thing. Let me assign the result to empty array, meaning we have to store the match start indices, right? So next let's go with the index. Let's go with the index for text as well as let's go with the index for the pattern. So I'll just go with I equals 0 and also j equals 0. This is fine. Finally, let me go with a while loop here. While I less than n. Simple. Now, within the while loop, what should I do? Suppose if there is a character match, right? Or the if characters match, then we have to move both the indices forward, right? So let's write the simple if condition for that. So this one will be text of I if it is equal to pattern of j, then what I need to do? So this is if condition, right? So then I have to increment I equals I plus 1 and also j equals j plus 1. This is also simple. Now let's do one thing. If we have matched entire pattern, then we have to record the match. So if, so this one j equals what do we call, m. So in that case, what we need to do, we have to match the starting index that is equivalent to the current I minus pattern length, right? So I'll just go with the append. So this is append of I minus j. This is fine. J equals, so let me go with the LPS here of within the array. Let me pass j minus 1. This is fine, man. Now let me go with the else here. So this one, else it has to match the if, right? So yeah, this is fine, man. Else what we need to do here, so suppose if the characters mismatch. So previously what in the if condition we have written, if suppose if the characters match, then we have successfully moved the both indices forward. Now suppose if there is a mismatch in the characters, then what we need to do, we are making use of the sliding window, right? Two pointers pattern, as I've said in the this one definition. So now we have to go with the slide pattern using the LPS, nothing but the longest possible suffix, to avoid the rechecking text characters, right? So this one, so this is for the mismatch case. Suppose if j not equal to 0, then we have to slide the pattern using LPS to avoid the rechecking text characters. So j equals LPS of, so this one will be j minus 1, right? So this is fine. I'll just go with else here. So we are going with a no partial match to fall back to, nothing but advanced text, right? So I'll just go with I equals I plus 1. Simple, right? So finally what we will do, we have to return the result, right? So we have to return the result. So I'll just go with return result, right? So we are done with the algorithm part. We are done with algorithm part. Now let's go with the testing, or let's go with the example usage here. So let me pass some text man here. So this one I'll just give here text equals. So within the strings, let me go with a b. So some random characters I'll give. I'll just go with d a b a. This one c d a b. This is fine. D a b. Then let me go with a b c a a b c a. B A B. This is fine. Some random. I'll stop it here. So this is nothing but the example haystack, right? So we know this. Let me go with a pattern. So this is equivalent to. So I'll just go with A B. Again A B C. This one A B A B. This is fine. Now we went with the example haystack as well as the example needle. So this pattern is nothing but the example needle. This we know. Let's go with the print. We have to print something for the interactive purpose, right? So I'll just go with the print here. So this is fine. Let me go with text. So this is also fine. Let me go with this one, text here. Now again let me go with print here. So let's print the pattern here first. So this one has to be pattern. We are just we are just printing the text and the pattern man first, right? So I'll just pass the pattern here. This is also fine. Now for the build, I'll just write something within the strings that says, right? So I'll just go with slash first, followed by uh, building LPS array for the pattern. I'll just go with for the pattern. This is fine. I hope this part is clear, man. This one, let me assign the longest possible suffix to. Let me give here build LPS. This is also fine. Let me go with pattern. Yep. Now let me go with the print again. So this one will be LPS array. Let me do one thing. Let me pass LPS here. This is fine. This is also fine, man. We are just showing the LPS array values here, right? So print. So this one will be slash n. Let me go with searching. So for pattern occurrence. So I'll just go with pattern occurrence, occurrences, right? So this is fine, man. Pattern occurrences. So this is fine. Now let me go with matches. This one will be KMP search. So let me pass text as well as the pattern. So this is fine. Now let me go with the print here. Print. Let me pass something. Hmm, or let me write something here. Match starting from or match starting indices. So this is zero based, right? So let me mention that one as well. Not necessary, but I'll just give here zero based. So what the heck did I give, man? Zero. So so sleepy. So this is fine. Zero based. I'll just give here. This is zero based, right? So this is fine. Now let me pass matches here. We have made use of the matches here, right? So finally, let me make use of the for loop here. Particular index. Uh, and basically matches, right? So matches. So let's print something here. Print. We'll be making use of string interpolation here. So let me go with if here. So match at. So this one will be index. So let me pass something within the index. This is fine. So now let me do one thing. So this is mm, uh, let's do one thing. Let me go with a single inverted comma, or let's go with the backticks, right? So this is fine, man. Let me pass something here. We have text. This is fine. Text within this one. Let me pass index within the array along with index plus pattern length. So this will be length of the pattern. This one we have to pass within the parenthesis, right? So this is fine, man. Yup. Mm, so oh, I have closed the this one here itself. Wow. So let me close this one here. String. Now this is fine, I believe, right? So now this is fine, man. So let me format the code once we are done with the algorithm, right? So we have made use of the print just for the sake of this one. What do we call interactive purpose, right? So the output that we need to get here is basically text and pattern first we are printing here, right? So this one we need to get first, right? So second, what we are doing here, text and pattern we are done. So building LPS array for the pattern, and we are displaying the LPS array, right? So we are displaying the longest possible suffix array. So this would be accordingly with whatever we have here. This would be actually uh, 0 0 1 2 0 1 2 3 4, right? So this is LPS array basically, right? So we have to get in the form of number basically. See here, LPS array, we are passing the LPS. So build basically. This is fine. Now we are going with the searching for the pattern occurrence. This one, searching for the pattern occurrences. So we are passing the KMP, this one, search function, right? So match has to start from the index 0, right? So this one actually 0 based, right? So this one has to be 10 accordingly with me. See here, pattern we give 3 plus 6, 9 here. This one, actually, yeah, 1 second, 4, 5, 6, 7, 9. And one more thing, 10. Yeah, as it is 0 best index, so this one we have to get 10 here. This is fine. Now 10 uh, along with it, so we have going with a match at index 10, right? So we are going with a match at index 10. So see here, if you are trying to match this one ABA, BCA, this one BAB, then we have to find this one within the text, right? So ABA we have found. This one is straightforward. ABA, first three letters. See here, ABA and ABA we have found. B also we have found. So next B, four first characters, this is fine. Then we have C. C is present here, right? So we have to check till here, right? So this is fine. C we have found here. This is fine. Now BC is fine. Next we have to go with A. A is present here itself, right? ABAB, this one. A. This is also fine. C A we have found. Finally B A B, right? So B we will find here. A also we will find next to that one. B A B B, this one is here, right? So we will be searching from here to here. Just give me a second here until this one. Let me remove this one. This is not required basically. So this now count the letters 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 basically, right? So including this one, these two we will exclude, right? So this one D is not required, basically D is not required for us, and also again A is not required, right? So basically this will be 0 to 9, nothing but 10 here in this case, right? So nothing but 10 here. So we have to give here match at index 10, match at index 10, nothing but we are printing this one. What do we call pattern basically, right? AB, ABC, this one AB, ABC, AB, AB, right? So AB, this is fine. Let me remove this one. Let me delete this one. So this is the output that we need to get. Again, let me explain this one line by line so you'll just understand this one better. So text, whatever I have given, this one shows the input text, nothing but this is nothing but hashtag. So in simple terms, this shows the input text we searched in, right? So this is the pattern, man. I have already said this one. This shows the pattern, nothing but the needle. We want to find the text. So this is the text that we need to find here. This is the pattern, right? So building LPS array for the pattern, whatever I have given here, this one, line number 76. So this, what it does, it indicates we compute the LPS array before searching, right? So LPS array, whatever I have given here, this one line number 78. So we are going with, this is nothing but this is the LPS array for the this one pattern AB, this one ABC, AB, AB. So this is for the pattern, this one. This is fine. Now from index 0, what happens here? 0, single character has no prefix, right? Single character has no prefix here. This one A, this has no prefix. And index 1, we are going with AB, right? So this time we are going with AB. This has no trivial path, trivial prefix that is equal to suffix, right? So this is fine. Next we will be going with ABA. ABA has A as prefix and the suffix. We know this. Now we will be considering ABAB, right? So ABAB has AB, right? Has AB as prefix, right? So this is fine. ABAB has AB. Now ABABC will be going with ABABC. We are having none here in this case, right? So we don't have ABC. So again, will the same thing will be doing with the from the index 5. So again, we'll be going with a A. So ABABC is done. So again, we'll start with A. So A, we have the prefix A for A. Next, we'll consider AB. We have the prefix for AB. Next, we have a prefix for ABA as well. So this one, the last three, ABA we will consider. So we already have the prefix ABA for the ABA. And finally, at the index 8, we have the prefix for ABAB, this one. So we will be going with ABAB. And this one, we have the prefix for ABAB, the final one ABAB. We have the prefix, right? So these values are what the search uses to jump J after the mismatch, right? So searching for the pattern occurrence, whatever I have given here in the line number 79, we began scanning the text using the LPS. Finally, the last two steps are matching starting at index, this one 0 best 10. Matching starting this one, whatever I have given. This one has to print 10 because KMP found one occurrence that is starting at index 10, right? So that one we have already discussed, right, in the text. So this is zero based indexing. That means the substring text 10 to 10 plus length pattern matches the pattern, right? So this one I have already showed. So finally, I'm going with a match at index 10, nothing but we are printing the pattern AB, ABC, ABAB, right? So this confirms that the match substring extracted from the text at index 10 is exactly the same pattern, right? So this is about the code that we have written. First build and then the search and then this one print for the interactivity example, simple one, right? So let me this one, let me do one thing. Let me come here, let me copy the file name. Let me do one thing, I'll just press Ctrl J. So I'll just give here Python. So this one file name dot py. So see here, uh, this is fine. Now we are going with a pattern. This one, what do we call? Pattern text that we have given, and the pattern also it is getting printed. So now we are stuck at this one, building LPS uh, array for the pattern. Right. So let's wait for some time. So there was indentation problem within the build actually. I just fixed it. So this is fine, man. Now let me come out of this one entirely. Let me run this one again. Yeah, now text we are getting this one, pattern the same thing, these two, and building LPS array for the pattern. LPS array we are getting correct, right? So 0 0 1 2 0 1 2 3 4. This is fine. Now searching for the pattern occurrences, we have already discussed this one. Match starting indices, nothing but this is 0 best, we have found it the 10 uh, that I have already explained. Finally, match at index 10. So this one we are along with this one we are printing the pattern as well, right? So along with the length we are printing the pattern as well, right? So this is fine. Now we have got the correct answer, right? So this is it for the KMP algorithm, right? So this is it for the KMP algorithm, very simple, right? So now as we are done with the KMP algorithm, let me summarize whatever we have learned so far, and then we can just move on with the next algorithm, nothing but Robin Carp algorithm, right? So these are the some of the important string based algorithms. So first, let me summarize whatever we have learned so far. So what KMP gives us basically, so it is deterministic, right? So we can just go with a big of n plus some worst case time string. So we can just search by pre-computing the longest possible suffix array or the LPS array to avoid the rechecking characters. Main thing that we make use of the KMP algorithm is for the optimization within the strings, so that we can pre-compute the LPS array to avoid the rechecking characters. To avoid rechecking characters, main thing. Many a times when we are giving this thing, what do we call? Uh, Contest on this thing, what do we call, whether it may be LeetCode or whether it may be this one, Codeforces or the code chip, right, or the coder, anywhere. So if we are giving the contest, so most of the times when string based algorithms, when we have to optimize, it will be usually KMP or the Z algorithm, right? So extreme optimization. So that is the reason we'll be making use of the KMP. Just remember this one. So here again, so it will be big of n plus some on the worst case, right? So time complexity. So string search, so we'll be going with a string search by pre-computing an LPS array to avoid the rechecking characters. This is one thing. Space complexity would be big of m, right? So this is for the LPS table that we created, right? So this is fine. So when we will be making use of the this one KMP algorithm, so when we need the guaranteed linear time, exact substring search, right? So this will be basically useful in the text editors, right? So this will be very helpful in the text editors if you think of it correctly, right? So this will be very helpful in the text editors uh, along with the pattern matching utilities as well, and it will be very helpful in the competitive programming as well, right? So this is fine. Now what are the alternatives that we can make use of this one to the KMP algorithm? So we can just go with a Robin Karp algorithm, right? So the Robin Karp, basically it is a probabilistic rolling hash, right? So this is good for the multiple patterns, but uh, unlike KMP, it can have collisions, right? So this is probabilistic rolling hash algorithm, this one Robin Karp, but uh, it is good only for the multiple patterns, but it can have the collisions, right? So that is the reason most of the times we'll be going with the KMP itself, right, rather than the Robin Karp. So it will be naive. Basically, we can just go with a big of n into m. It's simple, very simple. Robin Karp is very simple, but it is very slow comparatively to the KMP. uh, we can just go with the suffix automation or the suffix arrays. We can just go for the suffix automation or the suffix arrays for the more complex queries, right? So this is it. These points you have to remember, man. We are done with the KMP algorithm. Next, as usual, we'll be discussing about the Rabin Karp algorithm, right? So for now, this is it. Thanks for watching, guys.